August 17th, 1999. Izmit, Turkey. A city wakes beneath the quiet surface of the earth, unaware that the ground beneath its buildings is about to change. At 3:02 in the morning, the North Anatolian fault ruptures. The earthquake lasts less than a minute, but in that time, solid ground becomes something far less reliable. Roads buckle, buildings collapse. Underground water and sediment are forced upward. In some places, the earth behaves almost like a liquid. This is not the most dangerous ground, because it is steep, unstable, or obviously broken. It is dangerous because it can look completely normal until the moment it fails. Across the planet, there are places where the surface beneath our feet can lose its strength with almost no warning. Some are built on loose sand. Some sit above hidden cavities. Some lie across active faults. Others are made dangerous by water, volcanic heat, collapsing rock, or pressure accumulating far below the surface. The most deceptive of these hazards is liquefaction. Normally, grains of sand and sediment press against one another and transfer the weight of everything above them into the ground. Water fills the tiny spaces between the grains. During strong shaking, those grains can rearrange. If the sediment is loose and saturated with water, the pressure inside the pores can rise dramatically. The grains lose contact with one another. The ground loses strength. For a short time, soil can behave less like solid earth and more like a dense fluid. Buildings may tilt without their foundations breaking. Roads can split and sink. Buried pipes can rise toward the surface because they are lighter than the surrounding saturated soil. Entire sections of land can move sideways toward rivers, coastlines, or lower ground. This process is called lateral spreading. The danger is not simply that the earth moves. The danger is that structures designed for stable ground are suddenly standing on something that is no longer stable. The 1964 Alaska earthquake showed how powerful this effect could become. The magnitude 9.2 earthquake shook southern Alaska for several minutes. In Anchorage, sections of the city were built on sensitive sediments. The shaking triggered landslides and ground failures, including the collapse of entire sections of developed land. One neighborhood moved dramatically toward the water, carrying houses and roads with it. The landscape itself had become part of the disaster. Something similar happened thousands of kilometers away during the 2011 earthquake in Japan. The magnitude 9.00 earthquake produced enormous shaking across the country. In parts of Tokyo and surrounding areas, reclaimed land and water-saturated sediment experienced liquefaction. Pavements deformed, buildings settled unevenly, underground infrastructure shifted. The earthquake was catastrophic for many reasons, but the damage revealed a broader truth. A city is only as stable as the ground supporting it, and modern cities increasingly occupy ground that nature never intended to carry them. Coastlines are filled. Wetlands are reclaimed, rivers are redirected, harbors are expanded. Sand and sediment are placed over waterlogged soils, then covered with roads, foundations, warehouses, towers, and entire neighborhoods. From the surface, the result can look permanent. Beneath it, the physical conditions may remain dangerously fragile. But liquefaction is only one form of dangerous ground. Another is ground that disappears. Sinkholes can develop when soluble rock beneath the surface is gradually dissolved by groundwater. Limestone is especially vulnerable because slightly acidic water can slowly enlarge cracks and cavities. For years, decades, or even centuries, the surface may remain intact while a hidden void grows below. Then something changes. A storm adds weight and water. Groundwater levels fall. Construction alters drainage. A weakened roof collapses. the surface drops into the cavity below. Sometimes the opening is small. Sometimes it becomes large enough to swallow vehicles, roads, or buildings. In 2010, a massive sinkhole appeared suddenly in Guatemala City after heavy rainfall from Tropical Storm Agatha. The circular cavity dropped deep into the urban landscape, revealing how quickly a hidden geological process can become a public emergency. But not every apparent hole is a natural sinkhole. Urban drainage failures, collapsed pipes, construction, and human alterations can also create cavities beneath roads. The distinction matters because the surface may conceal a completely different mechanism. Another kind of dangerous ground is created by moving ice. Glaciers can grind valleys, transport enormous quantities of rock, and reshape entire landscapes. When ice disappears, the terrain it leaves behind can remain unstable. Mountain slopes that were supported or constrained by glaciers can adjust after the ice retreats. Rockfalls and landslides can become more likely in some environments. The problem is not that glaciers simply melt. The problem is that removing millions of tons of ice changes the forces acting on the landscape. High mountains create another danger because gravity is constantly working against them. A mountain slope can remain apparently motionless while stress accumulates inside fractures. Water enters cracks. Ice expands and contracts. Temperature changes weaken rock. Earthquakes provide sudden disturbances. Eventually, gravity wins. A landslide can release millions of tons of material in seconds. Some of the largest landslides on Earth have moved entire mountainsides. When that material enters a lake, reservoir, or narrow valley, it can displace water and generate waves. In 1963, at the Vajont Dam in northern Italy, a huge landslide descended into the reservoir behind the dam. The water displaced by the slide surged over the dam and into the valley below. The dam itself remained standing, but the wave devastated communities downstream. The lesson was unsettling. A structure can perform exactly as designed and still be overwhelmed by a geological event occurring beside it. There are also places where the ground is dangerous because it is not merely unstable, but alive with heat and pressure. Volcanoes create some of the most extreme landscapes on Earth. Near an active volcanic system, apparently solid ground may hide magma, hot gases, unstable deposits, or underground hydrothermal systems. A volcanic eruption does not always begin with a dramatic column of ash. Sometimes the warning signs appear gradually. The ground rises. Small earthquakes become more frequent. Gas chemistry changes. Springs heat up. New cracks appear. Scientists watch these signals because the surface can conceal what is happening kilometers below. Volcanic ash creates another hazard. When deposited on steep slopes, it can mix with rain and become a fast-moving slurry called a lahar. A lahar can travel through valleys long after an eruption has ended. The danger, therefore, does not necessarily disappear when the volcano stops erupting. The landscape remembers the eruption through unstable layers of ash and rock. Water can turn those deposits into moving ground. In other environments, water creates dangerous ground without an earthquake or volcano. Permafrost contains soil and rock that has remained frozen for years, decades, or thousands of years. When permanently frozen ground thaws, the ice within it can melt and the soil can settle. Roads deform, buildings tilt, pipelines require new engineering, entire landscapes can develop depressions and irregular surfaces. The danger becomes increasingly important as high-latitude regions warm, because infrastructure built on frozen ground depends on conditions that may no longer remain constant. The ground is not simply a platform. It is part of a changing climate system. Then there are the places where the ground moves slowly enough to escape notice. Subsidence can occur over years or decades. Groundwater is pumped from underground aquifers. Sediment compacts. The surface gradually sinks. In some cities, the change can reach centimeters per year. The result is subtle at first. A road becomes uneven. A drainage system loses its original slope. Flooding becomes easier. Foundations settle. The problem becomes especially serious when subsidence combines with rising sea levels. A city that sinks while the ocean rises, effectively, loses elevation from both directions. Jakarta has faced severe subsidence in parts of the metropolitan region, driven by factors including groundwater extraction and the compression of sediments. The exact causes vary by location, but the principle is straightforward. Remove material or water from below, change the pressure, and the surface can respond. This is one reason why dangerous ground is not always an act of nature alone. Human decisions can amplify geological vulnerability. The same principle applies to earthquakes. Earthquakes cannot be prevented, but their consequences can be dramatically altered by where and how people build. A fault running through an empty landscape is a geological fact. A fault running beneath a densely populated city is a risk. A loose layer of saturated sand beneath a field is a natural condition. The same layer beneath a hospital is an engineering problem. This is why geologists and engineers study the ground before buildings rise. They map faults. They examine soil layers. They measure groundwater. They identify areas prone to landslides and liquefaction. They use seismic surveys, boreholes, satellite measurements, GPS networks, and instruments that detect tiny changes in the landscape. The goal is not to predict every collapse. It is to understand where failure is physically possible. Some of the most dangerous ground can therefore be identified without seeing the danger directly. Beneath a city, geological layers form a hidden architecture. Hard rock may sit beside soft sediment. Water may occupy old river channels. Buried faults may cut through foundations. Ancient shorelines may lie beneath modern neighborhoods. Former wetlands may have been filled and built upon. A map of the surface alone cannot reveal all of this. The most important layer of a city may be the one nobody sees. Earthquakes expose that hidden architecture. When seismic waves travel through different materials, they behave differently. Soft sediments can amplify certain types of shaking compared with hard bedrock. The same earthquake can therefore produce very different effects only a short distance apart. Two buildings with similar designs may experience very different forces because they stand on different ground. This phenomenon helped explain variations in earthquake damage during major disasters around the world. The danger is not determined only by the magnitude of the earthquake. It depends on distance, depth, duration, building design, and the geological conditions beneath each location. Even the shape of a basin can influence how seismic energy behaves. This makes the idea of the most dangerous ground more complicated than identifying one place on a map. There is no single patch of Earth that is always the most dangerous. Danger emerges from the interaction between geology, water, gravity, climate, construction, and time. A steep slope may be harmless until saturated by heavy rain. A flat field may become dangerous when an earthquake strikes. A stable foundation may become unstable after groundwater levels change. A volcanic valley may remain quiet for generations before an eruption or lahar transforms it. The ground can be dangerous because it moves quickly, but it can also be dangerous because it moves so slowly that people build on top of the change. And sometimes the greatest danger is not movement at all. It is uncertainty. We stand on the surface and see roads, houses, fields, bridges, and cities. Beneath them are layers formed over enormous periods of time. Some were deposited by rivers. Some were created by glaciers. Some were erupted from volcanoes. Some were crushed from mountains and carried toward the sea. Some contain water. Some contain cavities. Some contain faults that have been silent for centuries. The surface hides all of this complexity behind the illusion of permanence. That illusion is useful for everyday life. It is also dangerous, because the ground beneath us was never truly still. Continents move, mountains rise and erode, rivers migrate, sediments compact, faults accumulate strain, ice retreats, groundwater flows. Volcanoes breathe through fractures in the crust. On human timescales, these processes can appear invisible. Then, in a matter of seconds, decades, or centuries, the hidden movement becomes visible. The safest response is not fear of the ground, it is understanding. Dangerous ground leaves clues. Geological maps reveal faults. Soil studies reveal weak layers. Satellite measurements reveal deformation. Seismic instruments reveal earthquakes too small for humans to feel. Hydrological records reveal changes underground. Historical records reveal where earlier disasters occurred. Together, these clues allow scientists to transform invisible geological processes into measurable risk. And that changes the question. Instead of asking whether the ground will ever move, scientists ask where it is most likely to move, how it might fail, what could trigger it, and what stands above it when it does. That distinction has saved lives. Engineering can strengthen buildings. Drainage can reduce landslide risk. Foundations can be designed for difficult soils. Hazard maps can guide development away from the most unstable slopes. Monitoring systems can detect changes before a major eruption or landslide. None of these measures can make Earth completely safe. They can make societies less surprised by what Earth is capable of doing. The most dangerous ground on Earth is therefore not necessarily the ground that looks broken. It may be the perfectly ordinary ground beneath a city, a highway, a home, or a bridge. It may be the soil that feels solid under your feet this morning. It may be the sediment holding millions of liters of water beneath a neighborhood. It may be the mountain slope that has not moved for centuries. It may be the invisible fault beneath a quiet street. The greatest danger is hidden motion. And sometimes the ground only reveals its true nature when it is too late.